In our next section, we're going to look at doing MPLS traffic engineering with segment routing, and we'll see it's very, very similar to other examples that we've done previous with MPLS TE. Mainly the only thing that we need to do is under the traffic engineering tunnel, we need to specify that the path option is using segment routing. Whether that is an explicit option, we're specifying the hops or the interface or the label value, in our particular case, which would be essentially the segment ID. And in addition to that, we could have a dynamic path option that is using the segments as well. Okay, so in this section, we're first going to go through a brief overview of traffic engineering with segment routing, and then mainly be focusing on the configuration steps. Now, the main advantage here that we'll see when we're looking at traffic engineering with segment routing as opposed to just TE on its own is that we no longer have the requirement for the resource reservation protocol. Now, with RSVP TE, the big issue with scaling the network is that the devices in the middle need to maintain the state for the tunnels. So if I'm a P router and I have 100 different tunnels going through me, then normally for L3 VPN destinations, the P router would not have to know about that. But in the case of an RSVP tunnel, every device along the path has to have the reservation stored. So with segment routing, that's not the case. We'll see because of how these segments are encoded. Okay, the difference here is that the source routing is done by the PE that is ingressing the packet or doing the label imposition. So for example, if we're trying to go to node 3 via router 1 and router 2, the label stack would look like 16001, 16002, 16003, as opposed to pushing just one label on the stack and then having the midpoint having to do the swap operation, and it would have to swap as the tunnel comes in and as the tunnel goes out. So the idea here is that we're using multiple labels in the stack to define from the source what the end path is going to be. Now, ultimately going forward, the idea of this is that you're using an SDN controller, a software-defined networking controller, or what's called the path computation element in our particular case in order to make these decisions. So the idea is that the PCE would have the overall visibility of the network. It knows what are all the node SIDs, what are the adjacency SIDs, and then it would be able to make a decision. This is your path for low latency, this is your path for rerouting, and then it would push that information to the head NPE in order to insert the labels into the stack. Now, in our particular case, this is going to be outside of our scope, SDN with segment routing. So we're mainly just looking at this the same type of way that we've done traffic engineering in the past with MPLS, where we are going to configure an MPLS TE tunnel, and we're going to define the path option. Path option has our constraints. The only difference then is that we're specifying we're using segment routing for that path option as opposed to just regular RSVP TE. Okay, so in order to enable MPLS TE for segment routing, the steps are going to be very, very similar to what we've seen before. So first we need to go to all 6 nodes in the core. We need to globally enable traffic engineering on them. We need to go to every single interface that we're doing label switching on. We need to turn MPLS TE on there. And we need to go under our routing protocol. So either under OSPF or ISIS, enable TE there. And then last step is going to be on the head end. We're configuring the actual TE tunnel. So the difference here between the previous steps is that normally at the interface level, in addition to turning MPLS traffic engineering tunnels on, you would also have to say IP RSVP bandwidth. Or in the case of iOS XR, you would have the MPLS traffic engineering config, you would have the RSVP config, and they would be on a one-to-one basis with each other because every interface running TE needed RSVP to do the signaling. Okay, but in our case now, segment routing with the IGP extensions is going to be doing the signaling as opposed to a separate protocol. So in terms of advantages of using segment routing, this is the second one. The first one is that you're potentially getting rid of LDP. Second one is that we're potentially getting rid of RSVP, and then we're saving all of that core state by keeping the state on the edge devices with just the label stack. Okay, so let's go back to our topology diagram here. So again, we have our nodes on the bottom, routers 1, 2, and 3. and then our nodes XR1, XR2, XR3 at the top that we're going to be running traffic engineering on. Okay, so first thing we need to do, let's start at the bottom on the iOS nodes, and we need to globally turn TE on, and then we need to turn it on under the process. Okay, our final verification for this is going to be show MPLS traffic engineering topology. So similar to what we've done in other courses on TE here. Notice in this case it shows that it's blank, okay, because TE is off. So in global config we want MPLS traffic engineering tunnels, and then same config at the interface. So from router 1's point of view, this is going to be on interface gig 2.111, gig 2.112, and gig 2.12. Okay, so note here that we're not turning RSVP on, we're only turning MPLS traffic engineering tunnels on. Okay, same thing on router 2. So globally, MPLS traffic engineering tunnels, interface gig 2.12, gig 2.211, 212, 213, and 23. Okay, router 3, the same thing. Config T, MPLS traffic engineering tunnels, interface gig 2.23, gig 2.312, and 313. Okay, next step is we need to go under the routing process. So again, we enable MPLS globally, or excuse me, we enable TE globally. We turn it on the core facing interfaces, and then next step is under the IGB process. In this case, we're running ISIS routing. We need to enable it for level 2, which is the routing type that we have, and we need to set the router ID to be the loopback. So next on router 3, let's go to router ISIS 1. MPLS traffic engineering level 2, and the router ID is loopback 0. Okay, so same thing on routers 1 and 2. Router ISIS 1, MPLS traffic engineering, router ISIS 1, MPLS traffic engineering. Okay, if we now check from router 1's point of view and show MPLS traffic engineering topology, we should see that router 1 is participating, router 2 is participating, and router 3. Okay, in previous examples, how we had parsed this was to look at the show MPLS traffic engineering topology pipe to include the what was it here? The MPLS TE ID. MPLS TE ID. This is going to tell us who is participating in traffic engineering. Okay, so right now we see the bottom 3 nodes. What we're missing is the top 3 nodes. Okay, so in XR, we're going to do this in MPLS traffic engineering mode. So on XR1, we have interface gig 0000.111, 211, and 1112. Okay, XR2, MPLS traffic engineering globally. Then what interfaces? Interface gig 0000.1112, 112, 212, 312, and 1213. Okay, then lastly on XR3, MPLS traffic engineering tunnels, or just MPLS traffic engineering, interface gig 0000.1213, gig 0000.213, and 313. Okay, now that we have TE enabled globally, we have it enabled at the interface level. The next step is the routing process. So if we show run and go down towards the end, our routing process in this case is ISIS 1. So under router ISIS1, we go to, I want to say we go to the address family, IPv4 unicast, and MPLS, traffic engineering, there we go. Okay, traffic engineering level 2, and what is the router ID, loopback 0. So if we show config, this is what we need on the other boxes as well. Okay, XR2. Commit. XR3. Commit. Okay, if we now go back to router 1 and look at that same output, show MPLS traffic engineering topology, pipe to include the MPLS TE identifiers, we now see that we have all 6 nodes running traffic engineering. Okay, so next let's take a look at the documentation. So how specifically do we do segment routing, traffic engineering, different than regular TE? And this is under that same section of documentation we were looking at before, which is the segment routing configuration guide for the ASR1K. Okay, if we look under the book contents, so we have just the OSPF v2 node SID, which we were looking at before, the ISIS v4 node SID, which is the equivalent in ISIS, and now we're doing segment routing traffic engineering with ISIS. Okay, so how to configure. It says we need to configure a path option for the tunnel. Then these other things are not required. Okay, these are optional steps. Okay, so it says under the tunnel, you could configure a path option that is explicit, named foo, as long as it says segment routing at the end. Okay, you could do dynamic routing, like your IGP, like OSPF, as long as you say segment routing at the end. Okay, same one as for this one. I believe this one also means dynamic. Okay, so let's look at now what is the current flow of traffic as we're going from router 6 over to router 7, and then we're going to modify what that path is using. Okay, so let's go over to router 6 and first check, do we have IP reachability to our endpoint, which is 7777. Let's source this from 6666. Okay, yes, we have connectivity. And let's do a trace route. It says we're load balancing. So we're going between router 4 and router 5. Okay, between 4 and 5. And then we're going out to the 2 edge routers. Okay, to simplify this, let's go ahead and take router 4 out of the mix for now. So router 6 only has one exit, which is going to go to router 1. So on router 4, I'm just going to go to the main gig 2 interface and shut this down. Okay, so router 6 is going to take a minute to notice this. And if we trace, we would see that some of the traffic would be lost. But the packets going through router 1, they should be able to forward to the destination. Okay, this is going to be based on the IGP convergence of the customer network, because router 6 doesn't see that its local interface went down. We have to wait for the hello and the dead timer to expire. Okay, so in the meantime, let's go over to router 1 and let's configure a TE tunnel. Okay, in global config, we have interface tunnel 0. Okay, actually, let's make sure that's not used. Do show run interface tunnel 0. Okay, it is not used. So on interface tunnel 0, we are going to first shut the tunnel down. Okay, same type of verification steps as we looked at in other traffic engineering discussions, is that if you shut the tunnel down, the very end you bring it up. If the line protocol comes up, it means that the signaling was correct. If the link comes up, but protocol is down, so if it's up/down, then it means it was a problem with the signaling. Okay, hopefully in this case, not going to happen because we hopefully configured traffic engineering on all of the interfaces in the path. Okay, so on interface tunnel 0, what attributes do we have? We first have the tunnel mode. Okay, tunnel mode is not IP or not GRE anymore, it's MPLS traffic engineering. Okay, we're going to unnumber this from the loopback. tunnel source is the loopback, tunnel destination is going to be router 3333. Okay, the tunnel MPLS traffic engineering path option, we're going to create a explicit path. Okay, we'll call it SR-TE. The difference, though, is that this is going to be used for segment routing. Do show run interface tunnel 0. And in addition to that, we need to advertise the tunnel into our IGP. So tunnel MPLS traffic engineering auto route announce. Okay, so do show run interface tunnel 0. We have our config. Okay, next step, we're going to configure that path option before the interface comes up. So we have an IP explicit path. The name is SR-TE. And we're going to go, and actually first, before we do that, let's look at what direction router 6 is currently going. So we're going 1, 2, 3. Okay, pretty straightforward. So 1, 2, 3 at the bottom. So let's say that as the packets ingress on router 1, we're going to send them up to 11, then over to 12, then down to 2, then over to 3. Okay, so what is our next address? Next address is going to be 11, 11, 11, 11. After that, we're going to 12, 12, 12, 12, then to 2, 2, 2, 2, then finally to 3, 3, 3, 3. Okay, do show run interface tunnel 0, and then let's say on tunnel 0, no shut. Hopefully we see the line protocol come up. Okay, if we now look at the show MPLS forwarding table, it says we have a traffic engineering tunnel bound, view additional labeling info with the detail options. So let's say show MPLS traffic engineer or show MPLS forwarding table. Detail. And what was that input label? That input label was number 34. So 34, it has a label stack of 3 labels. Okay, this is different now than your normal traffic engineering. So we have 16.0.12, 16.0.02, 16.0.03. This is now the encoding to say go to XR2, then to router 2, then to router 3. Okay, so if we look at this from router 6's point of view, do the trace route. This looks more similar to a carrier supporting carrier config now, right? Where there's more than 3 labels in the stack. Traditionally, with traffic engineering, you would see 2 or 3 labels in the stack, 2 under normal circumstances, 3 if you're in the process of doing a fast reroute. But normally you would have 1 for your VPN and then 1 for your transport, regardless of whether we're talking about layer 3 VPN or layer 2 VPN. Now in this case, what's happening is we're saying that the final PE is router 3. In order to get to router 3, we need to go through router 2 and we need to go through router 12. Okay, 12 being XR2. So it's simply a different way of encoding the traffic engineering information, where previously we would just push one label onto the top of the stack and then forward out the interface. The next top device through RSVP would already know what the label is to swap it to the next exit interface, where in this case it's the head end, which is router 1, that's doing the full imposition. And notice in this case it's using 4 labels because we have to go through 1, 2, 3, 4 hops before we can get towards our final destination. So in summary, when we look at the path options here, or excuse me, when we look at the configuration here, there's not really a ton of difference between regular traffic engineering and segment routing traffic engineering. The functional differences would be that you don't need RSVP But assuming that you're already doing regular MPLS TE, you don't need to turn RSVP off. You can switch your tunnels from the previous RSVP TE signaled ones to segment routing ones simply by changing the path option. But that is going to be disruptive for the tunnel to tear down and then to rebuild.